the Kruskal-Wallis test. When we use one-way ANOVA technique to compare the means of 3 or more populations, we assume or we verify that each independent sample is selected from a population that is normally or approximately normally distributed. So we are using one-way ANOVA technique to compare 3 or more populations from normally distributed, from normal distribution, population from normal distribution, or at least approximately normally distributed. But you can't always be so lucky and being able to verify that population is normal. In such cases, you are going to use Kruskal-Wallis test. So when we don't know that populations are normal, we are doing the same thing one-way ANOVA does technique, and we compare 3 or more populations. Okay? Kruskal-Wallis test. That's what Kruskal-Wallis test does. Determine whether 3 or more samples were selected from the population having same distribution from, okay, 3 or more samples. Okay? Selected from populations having the same distribution. So Kruskal test is a non-parametric test that uses to determine whether 3 or more independent samples were selected from populations having same distribution. In such cases, null hypothesis for Kruskal-Wallis test have as follows. Null hypothesis, all of the population have same distribution. Okay? And alternative, at least one population has distribution that is different from others. Okay. These two conditions for using Kruskal-Wallis test are that each sample must be randomly selected and independent. Those are important things. Independent, randomly selected. Okay? And the size of each sample must be at least 5. If these conditions are met, then the sampling distribution from Kruskal-Wallis test is approximated by chi-square distribution with k minus 1 degrees of freedom, where k is the number of samples. Okay, so let's figure it out now how we can calculate Kruskal-Wallis test statistics. Given 3 or more independent samples, again, let me underline, I cannot underline enough, samples are independent, test statistics H for Kruskal-Wallis test is equal 12 over n times n plus 1, and this is a long formula where I would highly recommend you to write down what is represented what. K represent number of samples, this k index. If there are 3 samples, then it will be n1 plus n2 plus n3, right? So nth, I would write down like this because it looks like multiplication. No, it has to be as an index. Nth is the size of the ith sample. So it could be n1, it can be n2, it could be n3. N, uppercase N, is the sum of sample sizes. And our ith, it's going to be like this, the sum of ranks of the ith sample. Okay? So, what we are going to do in the case of performing a Kruskal-Wallis test. So let's go for it. First, we need to verify that samples are random and independent, and they have at least size of 5. Okay, identify null and alternative hypothesis, get level of significance, we have it. Degree of freedom, we are going to use k minus 1. K is a number of samples. Number of samples, if it's 3 samples, then it's going to be 2, right? And determine the critical value and the rejection region. So, if the samples are selected from populations having the same distribution, the sums of ranks will be approximately equal. And H will be small and the null hypothesis should not be rejected. If, however, samples are selected from populations not having the same distribution, having different distribution, then H will be large. What is H? It's our test statistics for Kruskal-Wallis Test, right? Then H will be large and null hypothesis should be rejected. So because the null hypothesis is rejected only when H is significantly large, then Kruskal-Wallis test is always going to be right tail test. Okay? Okay. So let's start performing Kruskal-Wallis test. And here is the formula we already know. 1 second. This is formula for test statistics for Kruskal-Wallis test. Okay. So we need to take all these 3 samples that we are going to have, combine them in as a data in ascending order, and rank this combined data. Make decision and do interpretation. So, example, you want to compare the number of crimes reported in 3 police precincts in the city. To do so, you randomly select 10 weeks for each precinct and record the number of crimes reported. The results are shown in the table next to slide. We'll get there. Alpha equals 0.01, 1%. Can you conclude that distribution of number of crimes reported at least in one precinct is different from others? Okay. Here is our number of crimes recording, and so we have 3 samples practically. Yes. And we want to test. We want to test the claim that there is a difference in number of crimes reported in 3 precincts. So where is our null hypothesis? Here we have the distribution of numbers of crimes is the same in all 3 precincts. And alternative, the numbers are different. So this is going to be, alternative is going to be our claim. So alpha is 0.01, degree of freedom, since we have 3 samples, we do 3 minus 1. Okay, we are going to use chi-square test. I will post it under this video. We are going to use chi-square test. Okay. Since the test is right tail, it's always going to be right tail. And I explained already why. So with alpha equals 0.01, degree of freedom equal 3 minus 1, then the critical value chi 0 squared is going to be equal 9.21. So here it is. If I show you, this is chi-square test, and we have alpha 0.1, 0.01. It's the column before the last one, and degree of freedom 2. It gives us negative 2. It gives us, I'm sorry, 9.210. It's the second row and the column before the last one. So 0.01 horizontally, you are looking for the alpha, and degree of freedom is 2. That gives you, intersection gives you 9.21. And that is our chi-square critical rejection area. Okay, this is our chi-squared rejection area. It's right here. Okay, all right. So from here, now let's figure out our test statistics. So the table shows combined data listed here in ascending order and corresponding ranks. So we have free samples and with their sample the number and ranks arranged. Okay, all the way till 30. Here it's cleaned, but if you go over, you will see there are total 30. Okay, and ranks are marked down where we have duplicate. So it's instead of 8 and 9, we put 8 and half, 8 and half. Okay, so from here, then for the sum of ranks, for each sample, we add all these ranks. Okay, let's say for the 101st one, this, and then goes down 8 and half, 8 and half, and so on. So we have 3 of them. So you calculate first one, R1 is 77. For sample, second sample, it's going to be 177. For the third one, 211. And test statistics for the Kruskal-Wallis is going to be 12. It's a formula, part of formula. Here is the entire formula divided by 33. The length of 3 samples, 10 each. So 30 plus 1 here, and then R1, 77 squared divided by N1, 10. So, and then minus 3 times N is 30 plus 1, and you get your result. Okay, this is our test statistics. So we have test statistics 1252, and where is it? And our the rejection region, critical value 9.210. So it's falling in the rejection area. Therefore, we said that we decide to reject the null hypothesis. Yes? Okay, because, here it is, another the one more case. Very good. So we reject null hypothesis. We have here 12.52, and this is 9.21, which means it's in the rejected area. So since we reject null hypothesis and our claim is, this is our claim, alternative hypothesis, so which means we fail to reject, which means we say that with 1% level of significance, there is enough evidence to support the claim that the distribution of the number of crimes reported in at least one precinct is different from the other. Okay? And that's all. So using Kruskal-Wallis test to determine whether 3 or more samples were taken from the population having same distribution, not normal, because if it would be normal, we would use one-way ANOVA. Okay? And I'm done.